So good morning, and I am Dr. Anita. I am professor and principal of Alpha College of Engineering. So today I want to present a very small introduction on operational amplifiers. So op-amps, as they are commonly called, they come under the group of linear operational amplifiers. So these come under a classification of analog ICs. So if I were to define an op-amp is defined as a high gain direct coupled amplifier. So the gain of the op-amp is supposed to be very high, almost equivalent to infinity. Now when we come down to the schematic diagram of the operational amplifier, so this is the representation of an op-amp. An op-amp is supposed to have 5 inputs or outputs. So the input is, the first input is called as the inverting input, then we have a non-inverting input, and then we have an output. There are 2 power supply terminals, one is for positive power supply and the second is for the negative power supply. Now we go in for the third point that is to be discussed, and that is why an op-amp is called so. An op-amp is called so, or an op-amp is an operational amplifier. Why do we call it so? It is used to perform a number of mathematical operations like addition, subtraction, multiplication, division, integration, filtering, etc. So that is the reason why we call it as an operational amplifier. Any op-amp has got what are called as ideal characteristics. The ideal characteristics of the op-amp are listed as below. The first ideal characteristic is that the output impedance of an op-amp is going to be equal to 0. So when I say that the output impedance of an op-amp is 0, it indicates that the output is going to be very, very high. Whatever may be the input, we are able to get a very high output because the output impedance is going to be equal to 0. The second ideal characteristic is input impedance. The input impedance of an op-amp is supposed to be infinity. So the implication is that whenever an input is given, or even if almost 0 input is given, still the output will become a very high value. So that is the meaning of Zn equal to infinity. The third is open loop gain. The open loop gain of an op-amp is going to be equal to infinity. So it means that gain generally is output divided by the input. So when the input is very low and if the output is very high, automatically the open loop gain will be equal to infinity. The fourth ideal characteristic is the bandwidth. The bandwidth of an op-amp is equal to infinity. So this means that over the entire frequency spectrum, we are going to have a constant output, which implies that the bandwidth is equal to infinity. The fifth characteristic, ideal characteristic, is the characteristics do not drift with temperature. So drifting means usually for any electronic device or instrument, as the temperature varies, there will be changes in the characteristic of the device. But here when we say that there are no cases of drifting, it implies that as the temperature varies over a period of time also, there won't be any changes in the characteristic of the op-amp. So these are called as the ideal characteristics, and generally when we see all the ideal characteristics, they are either 0 or they are going to be equal to infinity. So now we'll come down to what are called as the op-amp configurations. So here we can go in for 3 types of configurations. The first one I will call as the inverting configuration. The second is called as the non-inverting configuration, and the third is called as the differential configuration. So now if we were to look back at the schematic diagram of this op-amp, using this I will explain the inverting configuration. Any op-amp schematic, if you see, has 2 inputs. One is the inverting input and the second is the non-inverting input. If the non-inverting terminal is going to be grounded, and if the input is fed only to the inverting terminal, it is called as inverting configuration. So if this terminal is going to be grounded and if the input is fed only to the inverting input, then we call it as inverting configuration. The second configuration is called as non-inverting configuration, which means that I provide the input to the non-inverting terminal. So if input is given here and the inverting terminal is grounded, then this is called as the non-inverting configuration. The third is the differential configuration. So we go in for the third option where both the inputs are going to be used. So I am going to give the input both at the inverting input terminal as well as at the non-inverting input terminal. So none of the inputs are grounded. Here this will be called as the differential configuration. So I'll just give some examples for all these three types of configurations. So for the inverting configuration, the input is going to be given to the inverting terminal. I am going to connect a resistor to the inverting terminal. A feedback resistor is going to be connected and we connect this to the output. The non-inverting terminal is grounded. So this resistor that is connected to the inverting input I will call as Rin because it is the input resistance. This resistor will be called as RF feedback resistance as it is connected to the feedback. So this configuration is called as inverting configuration wherein the non-inverting terminal is grounded and input is fed to the inverting terminal. So such a circuit is called as an inverting amplifier. So anywhere in linear integrated circuits, if the non-inverting terminal is grounded and if the input is fed to the inverting terminal, it will be called as inverting configuration. The specialty of this inverting configuration is whatever input is fed in, it will be inverted or it will have a phase shift of 180 degrees when it reaches the output. So if I give a square wave like this, at the input, it will be inverted as well as amplified and you will get a larger square wave at the output. So this is the inverting configuration. The second type of configuration I will call as the non-inverting configuration. So in the non-inverting configuration, the input should be given to the non-inverting terminal. So Vin is going to be given to the non-inverting terminal and the inverting terminal has to be grounded. So we will retain the input resistance and the feedback resistance as it is. I have just made a small change in the circuit. The input is given to the inverting terminal and the the input is given to the non-inverting terminal and the inverting terminal is grounded. So here the feature of this circuit is whatever input is given will come to the output as it is with amplification. So here if I give a square wave input like this, the same square wave will be amplified and will come to the output without any phase change. The third configuration that we are going to see is the differential configuration. So here again I am retaining the same circuit, but here the input will be given to both the terminals. So I retain Rin and RF as it is. Another input V2 is going to be given. So now because I have two sets of resistors, I just rename the resistors as R1, R2. Here also I have another set of resistors called as R1 and R2. So when both the inputs are going to be used, it is called as differential configuration and the output will be a difference between these two input voltages. So it is going to be, let's say I have two voltages V1 and V2. output will be V2 minus V1. That is, whatever is the voltage here will come as it is. Whatever is the voltage given at the inverting terminal will be inverted and it will come as V2 minus V1. So I can say that this circuit is going to behave like a subtractor. So this is how an operational amplifier is going to perform different operations in different configurations. Thank you.